In this chapter and next chapter, we will see mesh convergence. As we all know, the mesh convergence is very important part of FEA process, be it a small model or big model, simple or complex assembly level model. We must perform mesh convergence. Then we need to proceed further in FEA. Basically, we perform mesh convergence study to know whether our mesh density is adequate enough to capture the stress gradients or not, and that defines the accuracy of our results. So mesh convergence is very important. So uh, before doing workshop, okay, let's try to understand the gradient error estimator, ARR, in Calculix. Okay, so based on this output, we will see how mesh convergence can be performed. So let's see the definition of ERR. This is available as a standard output in Calculix. It is computed based on difference between principal stresses at all integration points of an element. So for the relative element value is calculated as a ratio of largest absolute difference between three principal stresses of all integration points uh, divided by largest absolute principal stress. Now this definition is very long and large, not easy to understand. So let's try to break up the definition and understand with the example. So this is based on my understanding after reading Calculix documentation. Okay, so we will take this first order full integration hex element, which has 8 nodes, so 8 integration points. So the location of integration points are shown in figure. This is approximate location. Okay. So we know the integration point uh, stresses and strains are calculated at integration points. So they are more accurate at integration points, while we get the results at the nodes for post-processing purpose, which are basically extrapolated and averaged value from the integration points. Okay, so for contour purpose, for contour output and visualization purpose, uh, the softwares show the results at nodes, but basically the more accurate values are integration points. So we know we can get 6 stress components, and from that we can also calculate 3 principal stresses for each integration point. So for this hex element, we have 8 integration points, each integration points having 3 principal stresses. So we'll get 24 values of principal stresses for a single element. So let's see how ERR is computed. So first, relative element value. The numerator is absolute of difference between maximum and minimum of 24 principal stresses, okay, for this element. So let's understand the numerator. For example, let's take we have output values as 230, 240, minus 210, okay, minus 50, 0, 10, okay, 100, and so on. So there are 24 values we got for this single element. Okay. Now out of this, the maximum of is, for example, this is the maximum, okay, and minimum is by sign is this one. Okay. So the numerator is the difference between these, okay, divided by maximum of absolute. So in this case, absolute maximum is 240. It could be negative as well. Okay. If for example, if we have minus 250, then denominator will be 250. Okay, because we need to consider absolute value of all the values. So basically numerator is maximum minus minimum divided by maximum absolute. That's how the relative element value is calculated. And then we multiply with 100 to get element value in relative element value in percentage. So for each element we get relative element value. Now to get ERR at node, okay, we know the node is shared by several elements, for example this node. Okay. Now I am not drawing hex elements, just for understanding purpose. Okay. So let's say we want to get the relative element value for this node. Okay, and it is shared by these three elements, 1, 2, 3. Now the relative element value at node is the maximum of sharing elements. Okay, so out of these three values, whichever is maximum is reported at this node. So now we can understand from this definition the ERR, okay, which is reported at a node, okay, basically from the elements only. In a sense, this gradient error estimator is not error measure. Okay, it is something difference of principal stresses. So it is basically a measure of variation of principal stresses within element, because we are taking the values from the element integration points. Okay, for in this example 24 integration points. So within element we are taking. So it is basically a measure of variation or gradient of stresses within element. Okay, and it is also because it is reported at a node, we can also say that it is a measure of stress gradient between adjacent elements. So in a nutshell, ERR is a stress gradient estimator. Okay, by looking at ERR outputs, we can understand like how the stresses are varying from one element to another element, and how are the gradients to peak or to low gradients. That means if we see high ERR in our output, that means we are meshing with very few elements to capture high stress gradients. Okay, and that's the reason the few elements are not able to capture high gradients, so ERR is high. So now in next chapter we will see the demonstration or workshop, and using ERR we will see how to perform mesh convergence study.